In this video, I am going to discuss how you can use the R software to extract image data or create image data. So here is one sample image file that resides in my hard drive. This is called toucantrans.png. Now any such digital image consists of tiny pixels arranged as a matrix, and each pixel has a red component, a green component and a blue component. We want to extract the numerical values of those components. For this, R has a number of package. Since it is a PNG file, so I need the package called PNG. Had this been a JPEG image, in that case I will use a package called JPEG. I first need to install them using this install.packages command, but I have them installed already, so I shall merely load them into the current session. So I load library PNG. I will not need the JPEG for this particular image, but I will still load it because later I am going to show a JPEG example. Now this particular file resides in a folder called data, so I have to go there, set working directory, set wd data. I issue that command. Okay, I am already in the in the data folder, so that is why I do not have to enter it again. I am getting an error message. Okay, anyway, now I want to load this toucantrans.png file. The command is, the function is read png, notice the spelling. I will issue this command and I get something, all the numbers I read into an object called X, and I want to know the structure of the object by issuing the str command. This tells me that this is a three-dimensional array. The first dimension goes from 1 to 144, the next goes from 1 to 200, and the third goes from 1 to 4. Okay, so I'm going to explain all these things in a moment, but first let's see whether we can reproduce this on the screen using R. So I just write plot, then as.raster x. So x is nothing but a numerical array, a three-dimensional array. We need to convert it into something which can be plotted. So as.raster function of R does precisely that. So I do that and I indeed get that same image. Now you might be wondering what is happening here, because here I can see some checkered pattern because this is a semi-transparent image. So part of the image is transparent. In this case the background here is already white. So that is why you are seeing that white background through the transparent parts. That is why it looks just white. So these checkered patterns were not part of the image. That was part of the image viewing software that I was using. Okay, so now that we see this, let's take a quick look at this thing. So 1 to 144, what does that correspond to? Let's look at the same image using our image viewing software. It says properties. It says that height is 144 pixels, and indeed that is the number of rows because it is stored as a matrix. So number of rows are given first, 144 rows and 200 columns. So its width is 200. So traditionally when we mention the size, we usually mention the width first and the height next. So it is a 200 by 144 image. But here they follow the matrix notation, number of rows first followed by number of columns. Now what is this 1 to 4? Well, every pixel consists of actually 4 numbers. These correspond to the red component, the green component, the blue component, the so-called RGB, and the alpha component, which gives you the transparency level. So when the alpha component is 1, it is fully opaque, and when the alpha component is 0, then it is fully transparent. For example, in these checkered places, it is equal to 0. Here it is somewhere between 0 and 1, so you can kind of see the checkered pattern peeping through. And you can get all those numbers and you can do whatever you want to do with them. Now let's see how we can pick up one particular region of an image. Suppose I want to plot not everything but only pixel values which lie between, that is pixel range that lies between in X lim, that is in the horizontal direction columns, 105 to 110, and in Y lim 80 to 86. So I issue that command, and now you can see clearly the various tiles, the pixels. So these are the pixels that I was talking about. So when you really want to zoom closely, you will see this. Now typically when you zoom in using some image viewing software, you will not see the pixels clearly because they try to blur the thing such that it looks beautiful. Not the best option when you want to do mathematical analysis, but when you just want to view it. R also has that feature. Here I have written inter equals f, means interpolation is false. So you can turn on interpolation, which will smooth out the image, by inter equals true, which is also default. In that case, you see, you get a blurred thing. So you really do not feel that there are only a few pixels that you are looking at. By averaging them with different weights, you get a slew of different values. Anyway, in our case, we shall always use interpolation false. Okay, now we can take a look at the different color components. So X is a three-dimensional array, so every entry of X is referenced by three indices. For example, if I want to get the very top corner of X, let me go back to the original picture, that is this. Suppose I want to get this value, this kind of the boundary pixel, that's purely black. I can type 1, and I leave the last thing blank, which means I want to see all the components. Then I see it is 0, 0, 1, means the red is 0, green is 0, blue is 0, gives it a black color, and 1 means it's a fully opaque pixel, and that corresponds to this black border. And similarly, you can find different pixels. Now, when I want to see all the red components of all the pixels, I similarly use this thing. I put nothing before the comma here, so I want all my rows. Nothing after the first comma, I want all my columns, but in the color index, I only specify 1, and 1 is red, so it is always in the order red, green, blue, RGB. So this gives me only the intensity of the red component, and you get this. Now this might look weird because possibly you expected to see something red. In this case, the red component is red only because it is considered the first component. When there is only one component in the data, things are being shown in just gray level. So that's what you see. Now if you really want to see red as red, we can do that. And the technique for doing that will be to turn off everything else. So I take 2 and set forcefully that equal to 0. And similarly, I can set 3 and 3 forcefully as 0. I might just get rid of the transparency, in which case I will set 4 also as 0. Now only 1 survives, and I can issue this command. And I do not see anything because I have made a mistake. Let's just see. I will just load it once again. I just made a mistake, very silly mistake. The mistake that I did was I made everything transparent. So I wanted to do this, that was okay. I wanted to this, that was also okay. But here I should have 1. Now this line should work. Plot as dot raster x. Yes. So now I see all the reds as reds. Similarly, you can see the blue component, you can see the green component, etc. Okay. Now I can do the same story with a JPEG image. Basically the same thing, except that I have to use the read JPEG function. I'm not going to go into that because they are very similar. If you want, you can just read from the screen and try to do that. Instead, I will show you a technique by which you can identify the location of a particular pixel. For instance, here I may be interested in knowing exactly what is the value of this region, some particular pixel here, for which I can use the locator function. So I want for only one point, so I will use locator 1. Now let's watch what happens. If I take my mouse over the plot window, it is just an arrow. Now once I issue this locator command, two things happen. Number one, my prompt has not returned, so it is running, and this little this little symbol is being animated, which means R is running. And when now I take it over the plot window, it has turned into a crosshair. Okay, I take the crosshair to wherever I want and I click it once, and immediately you see that my prompt has returned. It has recorded where I have clicked, and that value is stored in P. So let's see what is inside P. P has a X value, P has a Y value according to the current coordinate system. Now it is a decimal thing because I have not clicked right at the center of any pixel or anything, so it has got some decimal component. I may want to look at that particular thing. So how do I do that? P. Remember, X gives me the column index and Y gives me the row index. So I had called it X. X was the three-dimensional array that I obtained from the image. From that, I will take $y. Remember, Y gives you the row, and similarly $x, that will give you the column, and I want all the pixels, and I can try this. So in this case, I get something like 1001. But if I think carefully, isn't that somewhat weird? That how can this be pure red? This does not look like pure red to me. Well, because there is a little problem. When I am thinking about rows, the smallest row is up there and you are going down. When you are thinking about it as Y, you are starting from here and going up in that direction. So when I clicked here, the pixel that is being shown is actually down here, which indeed is pure red. So I actually need to do a little bit of correction, and the correction is pretty simple. All that I have to do is I have to remember the height of this. Now what was the height? I forget. So let's quickly see the height. Dimension of X. The height means this first number of rows, 144. So what I will do is I will come to this and I will make it 144 minus this. And now indeed I see something which is 0.345, etc. Indeed that is not completely red. And these things are of course forcefully set to zeros and ones because I am looking at only the red channel. So now you can see how we can create how we can extract a particular pixel. Now it is also possible to create our own image mathematically. So let's quickly do that. Suppose I want to create an image which I call Y, and I create a new three-dimensional array. The command for that is array, and initially I make everything 0. I do not want any transparency, so I will just make dimension is, suppose I want to make it 100 by 200 by 3. So RGB. So right now everything is just black, pure black. Well, I do not like that. So what I want to do is 1, 1, 1. I will make the red thing equal to 1. Okay, I will make the red and green, 1 and 2 both 1. Now red and green light together makes yellow light. So let's see what I get. I will write plot as dot raster of Y, and I indeed get something which is yellow, and number of rows is 100 and number of column is equal to 200. Of course, here I used a flat color. You can use some mathematical formula by which you transition from one to the other, and you can create exotic stuffs, and then you will just get something which is possibly more interesting, and that's basically what I wanted to show in this video.